Okay. Today, I'm going to build a quantizer. This is a thing I built a couple of times before in various iterations, but I think I understand how to do it better now, so I'm going to try again. So once again, this is going to be mostly Rust, with a little bit of work in the live coding stuff at the end, just to make sure that what I built works. Should be, I don't think this will be real long, because what I'm going to build is it's not that complicated. Okay, so what I'm going to do is I'm just going to copy some boilerplate for, conveniently, this is about the simplest possible node. Going to be a quantizer. So I don't know. In the off chance someone doesn't know what a quantizer is a a module that takes an input signal that is continuous over some range and discretizes it, turns it into a signal that is at particular values. So the sort of classic thing in the modular world is something that takes an input signal which is continuous between, say, 0 and 5 volts in the hardware stuff, where every 1 volt, every one represents an octave, and values between 0 and 1 or 1 and 2 represent sort of notes within, or pitches within that octave. And then the quantizer will take those continuous values and snap them to the nearest note in a particular scale. So if I want, like, C major, right? And I gave a voltage of, 4.2 volts or something, like that would snap me to a note in the C major scale in the 4th octave, right? And it's super useful for turning sort of arbitrary values into something that has sort of musical content, rather than just sounding like random noise. And so for like generative patching and stuff, especially, they're super useful. And it's the thing I've missed in my attempts to make music with the system. So today we're going to make one. So what it needs to know is two things. It needs to know the scale of the input value, and it needs to know the values it's going to snap to. And so I'm going to follow basically the pattern from sort of standard hardware modular synths, which is that 1 volt per octave. In this case, I'm floating point numbers instead of volts, but it's the same idea. And where I have octaves 1 through 6 basically, and like you would in sort of standard musical ideas. And then within that, there's going to be a set of intervals somehow, and I'm actually a little unclear on what exactly that means, but we're going to figure it out as we work. But to do that, I need to store. So I'm going to assume the 1 volt per octave thing, the mod 1 basically, over my list of whatever values, And so that is just going to be built into the code. But the thing I need to configure is the values that I'm snapping to. And we're going to start with those just being floating point numbers. So I think that makes sense. And then this is going to need a constructor. Because of some limitations in the live coding language, I'm going to have, you're not going to be able to configure this part directly in the live coding. And I'll just have to build some sort of keywords that have particular scales built in, but that's fine for now. That's a thing I'll probably fix shortly because I'm starting to get irritated by it. So this is going to take a scale, and just for flexibility, we'll say that it takes a slice of floats. and returns itself. And that is going to be the struct values, even though this is always going to be a scale, probably, to be consistent in naming. Okay, so that's like the most basic constructor. And there we go. Okay. And now, okay, and so this quantizer is going to, I think this is, my inputs and outputs are going to be the same. So it's got one input port, which is that continuous value that it needs to discretize, one output port, which is the discrete value, the discretized value. And so that's fine, don't need to change that. But unlike identity, this is not an identity function. So so now here's where we have to think about what those values actually represent. So the simplest thing to do, which I think is wrong, I know is wrong, would be to just have a list of values, however long, and assume that those are uniformly spaced within the octave. So for example, I would say, like, I'm going to give you values, 1, 3, and 5, and I'm going to say that an octave is a doubling. So if you give me the value of 0.5, that's going to be in my first, quote unquote octave, and I'm going to return the middle value from that list, which I think was 3. And if you give me 1.5, that's the second octave. Then I'm going to be in the middle of that octave, and I'm going to get double that value, which would be 6. So that sort of works, but it doesn't really represent how scales are actually laid out in music, because they're not uniformly distributed like that. There's intervals, and we need to respect those intervals to make this useful. So that doesn't work. So instead, what I probably need to do is have these values represent the intervals in my scale. Which are, probably would be represented as multiples of the base value of that scale. So like 1.23 times whatever the base note of the root value of the octave. And then what I would do is I would find no, that's dumb. It might actually be interesting for doing like music theory informed stuff, but there's a simpler way of doing this. So what I'm going to do is I'm going to take in this is going to take in the frequency values. Frequency values within. No, does that still not work? How do I do this mapping? This is harder than I thought. I'm just not thinking about it clearly. Okay, let me just look at some stuff. Piano. Yeah, okay. So let's just. I want to be able to look at this. So what this is the frequencies of the notes in the major scale in octave 4, I think. So this is an example of the thing I want to quantize to. So I want to say if my input value is a value between 4 and 5, I think I want to grab one of these notes as appropriate, and if it's less than 4, I want to grab a halving of the note. If it's more than 4, I want to grab a doubling of the note. However many times you have to have or double. But how do I pick which note? Because in a previous implementation of this, I just did the thing where they're uniformly distributed over the input, and it's just not as useful. It doesn't work for this. So what I can do is I can say, so I pick a starting point. So whatever the lowest note in octave 0 is, which I'll have to look up what that is normally, but I think it's like 20 hertz or something. I think it's slightly below 20 hertz. It's just outside of the standard human hearing range. And then double that to get the top of that octave. Okay, I think this is right. So that gives me the frequency range within an octave. And so then I can, using that, I can find the frequency that an input value corresponds to, assuming that each mod 1, each time you add 1 to it, you're doubling the frequency. And then I can take a list like this, and I can snap it to the nearest value. Okay, I think that makes sense to me. So quickly, I'm going to look up what the standard lowest note in octave 0 is, because I want the frequency of that, which I don't currently know. So okay, so having looked this up for concert A equals 440, which is, whatever. I'm just going to pick a standard tuning and not worry about that, because life is too short. So my C0, so the lowest note in octave 0 is going to be that. And so based on that, I can now figure out what my values for all the octaves are, which is cool. So cool. Okay. And then I'm going to assume that this input is the frequencies in octave 0, which is a little awkward because you're not normally down that low, and so it's not what you're going to think about, but it's relatively easy to do the conversion. So I'm just going to make that assumption here. That will be fine. And then work from there. So let me figure out. So first to figure out what my octave is. So the octave equals my input. And it's the can it work in Rust? No, it doesn't. That is me thinking in Python. What is integer division in Rust? I guess. I'm sorry. That was dumb. What I want is just this. Okay. Let's pretend like that didn't happen. Okay. So now I know what octave I'm in. And this car and CDR, I'm using these inputs because when I first implemented this type, I thought it was clever. and that's just the old Lispy, first value, second value thing. I don't even remember what the abbreviation stand for. But it gets the first value out of a tuple, or the second value, and my tuples are always pairs, because I don't know, just how I wrote the type. Okay, so now I need the fractional part, which I'm going to call that. Okay, so now I know which octave I'm in and which note in that octave, or what frequency within that octave I'm in. Actually, do I need to split that? I probably don't. Well, no, I need to know what the octave is at least. But I don't actually need this part. So my frequency, this is my undiscretized frequency, is going to be the bottom of 0, octave 0. So this would be if the input value was 0, this is what I want as my output. And I'm going to add to that what the input value actually is. Something. And that is going to be, so for every octave above this, I want to double. So I actually want to raise something to the power? Is that actually what I want here? Okay. Let me think about this briefly. In a language, it's a little easier to do interactive stuff in. By which I mean a calculator. Okay, so what is my 16? And I want C in octave 4, which means I want to double that twice. Like that. Octave 4, double that 4 times. Yeah. Like that. And that seems right to me. So, okay, so what I want is I want to do this. Yes, that is what I want. So 2 to the power of whatever, and then if it's a fractional thing, there'll be something in that octave. Yeah, okay. That is what I want. So it's going to be this times 2. It's going to complain if I don't get the type. And then power of whatever that is. And if it's 0, if it's 1, if it's negative, I don't know what that means. So I think being error tolerant in this framework is actually good. So I want this to produce a sensible value. I think. In which case I'm just going to take the max of this and 0. So if it goes negative, it'll just be the lowest thing. I don't know if that really makes sense, but I think it's alright. Okay, so it gives me my undiscretized frequency. And now I need to discretize that. So I need to figure out, so this is where I need to know what octave I'm in. So let's just think about that. That octave tells me how many times I have to double each of these values. Okay, I'm just going to do the quick thing. There's probably a faster way to do this, but by quick I mean the easiest thing for me to think about. Difference equals 2. difference that is infinitely large. So I'm just going to do a stupid linear search through my list of values until I find the one that's closest. Since these are probably going to be ordered, I could do something quicker, but I don't know. And that may actually matter because this is obviously in a pretty tight loop. But I don't know, whatever. And then let's see, it is going to be something, whatever. Okay. And then for every value in values, again, I'm assuming these are the frequencies in octave 0. I'm going to take, shadow that with a new thing, which is that value times 2f, whatever my current octave is. Let's do this in both places so I'm consistent. Okay, so that takes a value in octave 0, moves it into whatever octave it actually needs to be in for this. And then give me a distance between the value and the actual frequency. And then I want the absolute value of that. Okay, so now if this is d equals d, and then freq equals d. Okay, so now at the end of this, so I calculate the distance between this value in my possible values in the current octave and the continuous value in the current octave, and I just find the one that's closest. And again, knowing that the list is ordered and stuff, I could do that in something smarter than linear search, but I think this will be fine. So having done that, I now have min-freq, which will contain something, since we start with a min-d of infinity, assuming there's any values at all in that list, there will be something other than 0 there. Even if it's 0 in like the most degenerate failure case of just like a badly configured quantizer, then the output's just 0, and that's garbage, but it's fine. Okay, and then that's just my result. That's all I need. And I think that's it. I think that's a quantizer. Cool. So that was not too bad, assuming I'm actually thinking about it well. So now let's make the dynamic language, or the light-coding version of this, which is going to be a call to this macro, but more complicated than most of these calls, because I need to somehow put that stuff into it. So what I'm going to need is I'm going to need a thing, and we're going to call it scale major. I don't like camel case, but that's fine. So this is where my lack of the ability to configure these kinds of non-modulated parameters inside the live coding language is awkward, because now like I have to sort of bake in every scale that I might want to quantize to, which obviously is not super useful. And that's so the ability to fix that, or the ability to do that in the live coding language, is a feature that I intend to add soon. Just haven't yet. Okay, so now since I'm just going to do what I need is an octave 0. I'm going to drop back to Python for a second. there's my list. And now I'm gonna transform this with what I need to do. I need to move it down down 4 octaves. And I'm going to do that by going v times 2 to the basic math that I should know. Or v in whatever that is. No. Really? I guess it is the right thing. Okay. Cool. Okay. So then that's the value that I actually want. Like that. It's going to want a slice. And maybe like that. Okay, cool. Scale major. All right, I think that's good. So let's just see if that compiles. I have a test of this. What did I call it? Called it and that did not compile. Why not? Because I'm not using the right syntax. Okay. Expected at least 1 repeat. Okay, that is from my parser, which maybe there's a typo in this example I prepped, so let's check that. Expected to repeat at least 1 time and 0 times. What? What have I got wrong here? This would be better if I had better error messages. Okay. So there's my basic value, or my basic patch, and currently not using the quantizer. So let's say I want to, actually, let's do this. I have an LFO, it's a P sign, like a 1 hertz LFO, and this is going to be between 0 and 1, but since I'm trying to work across multiple octaves, just for the sake of the example, 0 to 5, and so now that's going to be the frequency here. And that didn't work. Why not? You think you're running. Still haven't gotten used to this change when things have to be uppercase. That is. Okay, so that's doing what I expect. That's doing what I expect. Oh, is this just too quiet? Oh, no. Sorry, I am not as smart as I think I am. So this is the reason you're not hearing anything useful except that aliasing, I think, is because this is giving me my control value between 0 and 5, which means this is also an LFO. It's well below audible rate. So we must have the quantizer. Okay. So major scale. Okay. And my major scale. Let's take the LFO, and then I just realized I think I may have structured this a little bit wrong, but that didn't work. Why not? Something else. Scale major. Good for me, picking predictable names. Okay. Still not running. Why is that? It is this, right? Yep. Okay. And not printing anything. Why isn't that parsing? Because I think the fact that I'm not seeing anything logged implies that it's not parsing, which gives me my old debugging problem. I don't have good debugging. So I'm getting that this is wrong. When I define this, so when this is my parser for the language, when I define what it means to be a node constructor name, which is that scale major, I say that it needs to be an uppercase letter followed by nothing but lowercase letters. Okay. So, but if I want to support camel case, I need to also accept uppercase letters. Which I can't. I need to figure out these are not clonable. There must be a more elegant way of doing this, but I don't actually know how it works. Okay, so that's the thing I should look up at some point. So the problem is it just since this was actually an illegal node constructor name because it had that second capital. Okay, and that rumbling is it actually running? Which is what I expect. And now if we go. Okay. That sounds sort of unquantized to me, but maybe it's just, let's make its range smaller. So move it into, so this is between 0 and 1 plus 4, so between 4 and 5, rather than between 0 and 5. Okay, there. Now you can hear the individual notes. So if I, just to make that super clear, someday I'm going to start remembering that. We're going to say this is a sample and hold. And every time I write this, I forget which direction the arguments go in. I think it's value first, trigger second. Well, it's the other way around. It is the other way around. Someday I'm going to get that right. Cool. Okay. So now we're into this territory of interesting things you can do with quantizers, because like these are running at different rates, which affects what it sounds like. That. I guess you need it to be usually prime, maybe, dude. Right. You know, and then you can do like, hey, what if I want 2 octaves? Okay, yeah. So this is, hopefully you can hear how, if you haven't heard people using quantizers before, how you can use this to get something that is melodic, but still random, or procedural, if not actually random, because there's no actual noise in this. Okay, cool. I'm pleased with it. So earlier I had a thought that I was maybe doing this wrong, because this quantizer takes 0 to 1. One. I'm going to say 1 volt because that's what I'm used to hearing, even though these aren't actually voltages. 1 volt per octave inputs and returns and outputs frequencies, which is not the way this would work in a normal like hardware modular rack, where it would take continuous 1 volt per octave and output discretized 1 volt per octave. But it would stay in 1 volt per octave, and then the oscillator is the thing that moves it to a frequency. My oscillators assume frequencies rather than 1 volt per octave. That may actually be just a fundamental design mistake I've made in building these things. It could be that the regular modular people are right. Or that I should go the other direction, and that this quantizer should take a continuous frequency in, and output a continuous frequency. I could also do it that way. But I'm not sure what the right thing is. And I'm just going to play with it like this for a while and see how it feels. And if I make changes, that will happen later. Okay, cool. I think I'm done.